Hello and welcome to my video. This is the second video of the Sequence Week series, so if you haven't seen my first video of the week, please check that in top right corner. Today we are going to solve the following problem. Consider a geometric sequence an with common ratio r is not equal to 1 and all terms of an are non-zero. Now define Sn as simply the partial sum, the sum of first n terms of the given geometric sequence an, and Pn is the product of the first n terms of the sequence an, and finally Hn is the sum of the reciprocals of each term of sequence an. Alright, so each definition is pretty clear. Now, what is the relation between Sn, Pn, and Hn? How these three sums or products are related? Okay, let's find that out. We want the simplest expression, so let's just let a1 as a. Then we already have a famous formula for Sn, the partial sum of the geometric sequence. The first term is a, the second term is ar, and the third term is ar squared, and the nth term is ar to the power of n minus 1. And this sum is given as a times r to the power of n minus 1 over r minus 1. So this a is first term, and this r is common ratio of the geometric sequence, and this n means number of terms, in this case n. This is the famous formula for the finite sum of the geometric sequence. If the magnitude of the common ratio r is less than 1, and if we let n goes to infinity, then we obtain the limit of Sn as simply a over 1 minus r, the famous formula for the geometric series. Right, so this is the expression for Sn. Now let's take a look at Pn, the finite product. Here the first term is a, and the second term is ar, and the third term is ar squared, and the nth term is ar to the power of n minus 1. Therefore, if you count the number of a's, we have total n a's, so we have a to the power of n, then we have r times r squared times all the way up to r to the power of n minus 1. So their exponents must be added. So therefore we have r to the power 1 plus 2 plus ... plus, and finally n minus 1. Now this is the sum of arithmetic sequence, which is simply n times n minus 1 over 2. So therefore we have a to the power of n times r to the power of n minus 1 over 2. So this is the expression for Pn. Now what about Hn? Again, if we write each term of Hn, we have 1 over a, and 1 over the second term a2 is ar, and 1 over the third term is ar squared plus ... plus, and 1 over an is a times r to the power of n minus 1. Therefore, the sequence 1 over an is also a geometric sequence with 1 over a as the first term and 1 over r as the common ratio. Therefore, for its partial sum Hn, we can apply the similar formula for Sn with only different first term and the common ratio. Therefore, Hn is the first term is now 1 over a, and the common ratio is now 1 over r, so we have 1 over r to the power of n here minus 1 over 1 over r minus 1. Now let's multiply r to the power of n at both numerator and denominator. Then we have, for this a, let's send it down to the denominator, and at the numerator, we simply have 1 minus r to the power of n, and in the denominator, we have r to the power of n minus 1 minus r to the power of n. So we have 1 minus r to the power n, and if we extract r to the power of n minus 1 here, then we have 1 minus r here. Notice something here. The Sn part appears in the expression, namely in this part. So this part, n plus a consists of Sn, and since we have a here, the denominator now must be a squared, and we have this part remaining, so we have r to the n minus 1. So this is the expression for Hn. So if we rewrite it, Hn and Sn are related like this, and Pn is given as a to the n r to the n minus 1 over 2. So from here, let's send this Hn down to the denominator and move these terms up here. Then Sn over Hn is given as a square r to the n minus 1. Now let's raise to the power n. Then we have Sn over Hn to the power of n is, if you multiply n here, we have a to the power of 2n times r to the power of n times n minus 1. And now you can see that the expression for Pn appears. So this is basically a to the n r to the n minus 1 over 2 squared, which is Pn squared. Therefore, we finally have our relation, which is Pn squared equals Sn over Hn to the power of n. And this is the relation that we are looking for. Now, some of you might want to take square root of this expression to write Pn equals Sn over Hn to the power of n over 2, which is equivalent to square root of Sn over Hn to the power of n. But this is not always true, because you see, if you want to write like this, then it must be guaranteed that both Pn and Sn over Hn to the power of n must be non-negative. But that might not always be the case. If you only take a look at Pn here, you can already see that Pn might not always be positive. More specifically, if Pn contains even number of negative terms, then Pn is positive, and if Pn contains odd number of negative terms, then Pn becomes negative. So remember that a squared equals b squared does not always mean a equals b. And that's all for this video. Again, if you haven't seen my previous video about sequence, please check that in top right corner. And also please like and subscribe to my channel to explore more math videos. And I will see you in another video.